We are in section 10.8. In section 10.8, we're going to finish the chapter by topic of complex numbers. And here is a page of the homework exercises for you. The ones that are highlighted are the ones that are on your homework sheets. So you can take a look at those, and of course, you can do as many of these as you like. These are the bare minimums I usually assign as a guide for your exams. So again, here I have excerpts from the textbook, and these are the homework problems. And we will do quite a few exercises like the ones that are highlighted. So let's begin our lecture by the following. Earlier in Chapter 10, I believe it was the first section of Chapter 10 when we first introduced the idea of square roots. We mentioned that the radicand, what's under the radical sign, has to be positive, because if I have something like square root of -4 here, in section 10.1 we said that this square root is not real, simply because I cannot multiply a number by itself and it turns out to be negative. And we left it at that. Now, in this section, we're going to actually do a little bit more with it. Now, keep in mind, no matter what we do with this, square root of -4, for example, we're not going to suddenly turn it into something that is real. So, it is not real, the square root of negative numbers. They're not real. But we would like to kind of rewrite them in another form, okay, and then pursue that further. So here what I have done is I rewrote square root of -4 as square root of 4 times square root of -1. And square root of 4, of course, is 2. And square root of -1 still not real. True? So again, as I was saying, this is not a way to get around the unrealness of square root of -4. So let's move on further now. So at this point, what the mathematicians have done is the following. They define the number I as a unique number so that it represents the square root of -1. And here the letter I stands for imaginary. Now, this number I, is again square root of -1, and it is in such a way that when you square it, I squared and I squared should be -1. Notice now, I squared -1. This part is actually real. The square of this imaginary number is real. So this is how this number I is defined. Now, using this definition of I, we can actually go back and finish off the example that we just displayed. So we can write the square root of -4 as 2i. And again, this is not real. It's just another notation for the not real answer to square root of -4. Now, because we have this I business now, the way I is defined, actually it turns out that the whole set of number system is defined based on this imaginary unit I. And these numbers are called complex numbers. So here is the definition of what a complex number is. A complex number, again, is going to be any number that can be written in this form, in green, a plus bi. Now remember, I is a square root of -1. And a and b here, by the way, these are actually real numbers. Okay, so a and b must be real numbers. So once we have defined it, then I can write several examples of numbers that are complex numbers. Now I've just made these up, and you can kind of see. The number that's before I can be any real number. Could be rational, irrational, decimal, fraction, negative, terminating decimal, non-terminating decimal, anything you desire, because it's got to be a real number. And of course, the a part is also a real number. Now, usually in this notation, by the way, maybe I just slide to the side. The a here, let me write that. A, it's called the real part of the complex number. And the bi, it's the imaginary part. So remember, every complex number has two parts. So there you go. That's usually what they call it. A is real, and bi would be the imaginary part of that. Now, please note that because of the binary nature of complex numbers, you have a plus bi, so there are two parts to this, right? Two parts here. The binary nature of complex numbers, that these are binomials, means there are two terms, so we can treat them as binomials. And then the other idea here we have is the idea of conjugates. So the conjugate of a complex number, a plus bi, is going to be a minus bi, and vice versa. So that means the complex conjugate of a minus bi is going to be a plus bi. And then that's what that is. Now, let's take a look at powers of I here. Something interesting will unfold as we go through this. So we're going to go to I to the fourth power, okay, and see how we can work this thing. Now remember, by definition, I is the square root of -1, right? So that's what this is. And I squared is -1, the real part. I mean, not the real part, but it turns into real. So if I want to do I cubed, I can write that as I squared by I. And if I do I fourth, I can write that as I squared I squared. Now, I cubed I squared times I. Well, I squared is -1. I is just itself I. So I cubed is going to be -I. I to the fourth, which is I squared, that one is going to be -1 times -1, and the product is 1. Excuse me. So we can see that I to the fourth is actually, again, is going to be real. So it seems like certain powers of I shuffle back and forth between being real and then not real. And let me just, there you go, this is real. And of course, I cubed, still imaginary, right, -I. Now, what if I want to do higher powers of I? And that's what I've done here. So I to the 7th, it's going to be I to the 4th times I cubed. If you want, you can write it as I squared times I, and work it that way. But the way I have it, I wrote it as I to the 4th times I cubed. Usually with higher powers of I, we try to work with as many I to the 4th groups first, and then work with whatever is left over. I'll illustrate this in a minute. So I went in the form of I to the 4th times I cubed. Notice that there are 7 factors of I here. Now I to the 4th, of course, that's just 1, right? This is 1. I cubed is -I right up here. So this product is -I. So I to the 7th is -I. If I look at I to the 12th here, this is going to be, this is going to be I to the 4th cubed. And I to the 4th is 1, 1 cubed, 1. So I to the 12th is going to be real. What about I to the 68? Again, that's I to the 4th to the 17th power. And because 4 times 17 is 68, so that's going to be 1 to the 17th power, or just 1. And for higher powers, as far as like how many I to the 4s are in I68, I did a long division of 68, this exponent, 68 by 4, I got 17. In other words, there are 17 groups of size 4 in I to the 68. Each of those group of size 4, I fourth is 1. I have 17 ones, which the product would be 1. And there you go. Now, something like I to the 11th for this one, I to the 11th, this is going to be I to the 4th squared. That picks up 8 powers of 8 i's, 8 factors of I, and then 3 more for the total of 11 factors. I to the 4th is 1, 1 squared 1, times I cubed is -I, and I to the 11th is going to be -I. So this is how you work these higher powers. Exercise number 86, I think you're doing number 85. That's why I picked this one. In number 86, I have I to the 38. So again, I went I to the 4 to the 9. That picks up 36. And remember, this is how you work that. You go 38 divided by 4. That means I want to know how many groups of size 4 are there in 38. So if I go 9 times 4, that's 36, subtract, and the remainder is 2. That's why I have 2 remaining here, and I have 9 groups of size 4. I to the 4th is 1, 1 to the 9th is 1, 1 to any power is 1. And I squared is negative 1. So the product would be negative 1. And there you have it. Now, who actually uses this, by the way? A lot of formulas in both like your calculus courses and also applications in engineering, in particular electrical and electronics engineering. It works out to where they actually run into expressions involving imaginary units and complex numbers. So just to kind of point out who would use something like this. Now, as far as now we are concerned, complex numbers, remember we said these are numbers just like any other numbers. So if they are numbers, then we would like to be able to add, subtract, multiply, and divide them. And that's what we want to do near the tail end of this lecture. First, addition and subtraction. So here I have an example of addition. So I'm adding 2 plus 3i and 5 minus 2i. We're adding 2 complex numbers. So because they're binomials, it makes sense that we treat these as like terms. For example, the 2 and 5, those are 2 like numbers. So I combine them together. And then the i's combine together. The 3i and negative 2i combine together. And that will give you 7 plus I. That's 2 plus 5, 7, and 3i minus 2i makes I. So the result is going to be another complex number. How do we subtract them? Again, drawing inspiration from addition, we can see that we can subtract the real parts from each other, and we're going to subtract the imaginary parts from each other. So the real part is going to be 6 minus 9, and imaginary part is going to be negative I minus 11i, and that's what this is. And those, of course, combine to negative 3, negative 12i. Okay. Hopefully you follow that. That's really not too complicated. Pretty straightforward. Their addition subtraction is really simple, folks. You just combine like terms. Now, I'm sure what this keeps popping. Okay. Now let's take a look at the multiplication. So here I have an example of multiplication. Now remember, complex numbers are binomials. So when we multiply them, it's as if you want to multiply 2 binomials. And we can FOIL them together. Remember the FOIL method? Or just call it distributive property. We're going to distribute the binomial, the first binomial, to both terms of the second binomial. So doing so, that means I'm going to multiply 2 by 3. And I'm going to do 2 times negative 8. And that's how I got the first 2 terms. 2 by 3. And this 2 times 3 gave me 6. And 2 times negative 8 gave me negative 16i. Right? And then we do the next distribution. Correct? We do 5i times 3 and 5i times 8. Negative 8, that is. Negative 8i. So 5 times 3, that would be 15i, and then 5i, negative 8i, makes negative 40i squared. And there you go. We have 6, negative I. What I did next was actually I combined these two. These are like terms, so they combine into a negative I. Now, remember, I squared was negative 1. Because of that, I replace I squared with negative 1 down here. Next step. So now it has 6. The sum became negative I, and that's negative 40 times negative 1, which makes positive 40, and combines with a 6. Gives me 46. And there you go. That will be the answer to the multiplication. So we can FOIL them. How do we divide them now? Oh boy. The division of complex numbers is far from intuitive. And it's actually kind of a pain in the neck to do it. So you can see, you be the judge of that. There you go. This is how you actually divide them. So let me go step by step on how this was done. This is the original problem. We want to divide two complex numbers. One thing we could not do, you cannot divide 2 by 7, divide 3 by 2. We just can't do that. Okay, so how is it done? We actually forget the division problem, because we're going to actually multiply these two complex numbers by another complex number. And usually what we multiply by is the conjugate of the denominator, the conjugate of the bottom, the denominator. Conjugate of 7 plus 2i is 7 minus 2i. We're going to do top and the bottom. Now, in the denominator, these conjugates, 7, we're doing FOIL, top and the bottom. So we do 7 by 7, 7 by negative 2, 2i by 7, and 2i by negative 2i, and this is what you get next. Do the same thing in the numerator, FOIL them, and this is what you get on top. And then I combine like terms, replace the I squared with negative 1. Replace I squared down here with negative 1. So, in the numerator, negative 4i, negative 21i made negative 25i. And in the denominator, of course, here we have a pair of opposites. These two are opposites, so they add to 0. And I carry the arithmetic. 14, negative 6 is 8, negative 25i remains. In the denominator, negative 4 times negative 1 is 4, 4 and 49, 53. Now, next step, we can actually divide individually by 53. So that's 8 over 53, negative 25 over 53. We are allowed to do that. And to kind of show you, remember, if we have, for example, a over b plus c over b, we can write this as a plus c over b, correct? Common denominators. That's how we add fractions, isn't it? Now, go in this direction. Go from right to left. Okay, and we go from right to left. That means if I have something in the form of a binomial, in this case, a plus c over b, you can divide a by b, you can divide c by b. That's just breaking up the fraction. And that's exactly what I did here. I divided 8 by 53 and negative 25 by 53. And the form, the answer to this again is in the a plus bi. If you look at the answers for like even this one, a plus bi form, the emphasis is on the form a plus bi. So, and that's how you divide these complex numbers. Pretty strange, huh? Now, let's take a look at some of these exercises together. I'm trying to do ones like your homework problems now. In exercise number 10, square root of negative 9. So that's going to be square root of 9 times square root of negative 1, right? So square root of negative 1 is I. So anytime you have a square root with negative numbers or negative radicands, just turn the radicand positive and just put an I in front of the radical. And that's what this becomes. The square root of 9 is 3, and then we have 3 times I is 3i. And then let's take a look at next one. In this next one, we have 16, number 16. Negative of negative 17. Now, something you got to be careful. Negative of negative 17. Maybe I will write that. Okay, let me write that here. Negative of negative square root of negative 17 does not equal to 17. You cannot multiply negative times negative in the radicand and what's on the outside. Okay, so pretty much what we have to do is we got to keep the negative on the outside and just work the inside. Inside becomes square root of 17i, and notice the negative stays. And that's the final answer in this one. Next exercise. Number 28, we are adding two complex numbers. So I added the real parts and I added the imaginary parts again here. The real parts added became 13. The imaginary parts combined, negative 6 and 9 makes positive 3i. Exercise number 36 wants us to multiply. So we're doing 3i times 9i here, multiplication. So 3 times 9 is 27, and I makes I squared, which is negative 1, so the answer is negative 27. Again, even this is in the a plus bi form, everyone, right, isn't it? So here is the a plus bi form of number negative 7. Number negative 27, that's like negative 27 plus 0i. And you can just kind of see a is negative 27 and b is 0. So all there is here is just the real part, no imaginary part. Number 50, we are multiplying, and remember we FOIL multiplication, we FOIL them. And I did, and that's how you get the product. You can verify these. Something like number 62, where I actually have power exponent 3 plus 2i squared. First I write it as repeated multiplication. That's definition of 3 plus 2i squared. Means 3 plus 2i times itself. And then we FOIL them, don't we? And I did, and here's the FOIL. So the answer is going to be 5 plus 12i for this one. Number 70, we're doing a division. In number 70, the division is 3i divided by 4 plus 2i. So we're going to times it by the conjugate. Remember, if this is plus, the conjugate will be minus between the two terms. And of course, you do whatever, you multiply top, bottom by the same thing. So in the numerator, I distributed 3i times 4, got 12i. 3i times negative 2i made negative 6i squared. Remember, I squared is negative 1. And then in the denominator, I FOIL again. Now something, by the way, happens in the case of complex conjugate. This is the second time that this happened. If you look at the middle terms, the two middle terms add to 0, right? That's these two. So anytime you multiply complex conjugate, a plus bi times a minus bi, let me write that. When you do a plus bi times a minus bi, you can forego the o and the I in FOIL. Remember, FOIL is F-O-I-L, right? F-O-I-L. So that would be first, outer, inner, last. So instead of doing FOIL, you can actually just do first and last. That means just do a and a, you get a squared minus bb would be b squared, right? And of course the I and I makes I squared, which is negative 1, which forces this to be positive. So the product of complex conjugate, we just showed that it's a real, and it will be a squared plus b squared. But I went ahead and did FOIL just because most of you probably do that. And then carried on the arithmetic. In the denominator, you get 20. And my next step, of course, is to break it into two fractions, and I did. And then I reduced the fractions to lowest terms. 6/20th, divide the 2's out, you get 3/10. 12/20, divide the 4's out, you get 3/5. And there you have it for number 70. And let's take a look at number 72. In number 72, we're dividing 4 divided by 7i. So what I did actually here, the problem was just this part. So I multiplied top bottom by 7i. And actually the conjugate would have been negative 7i, but that's okay. In number 72, let me make sure that that is indeed the problem. Yeah. And let's see. So let me just do what we said. Let me multiply by conjugate, but the answer should be the same. So multiply top bottom by negative 7i. The bottom is going to be negative 49, right? Negative 49i squared. And I squared is negative 1 times negative 49 makes 49. So the next step is correct. That's just 49, right? So notice how I carried that negative throughout. And then these double negative made 49 positive. Now in the numerator, we have 4 times negative 7i. That's going to be what? Negative 28, right? Negative 28i. And then that's negative 28i, and you can kind of see now that negative 28, you can put the negative in front of the fraction line. So it didn't matter in this one. But if it was a plus bi form, I would have to multiply by conjugate. This one, it didn't matter because there's no real part in the denominator. So I got away with it. And there you have it. And I believe this is next to the last problem. We're going to look at a division. Now with division, when 28/49, let me actually back up here, folks. I just realized 4 times 7, 7 by 7. We can actually simplify this, couldn't we? Divide the 7, 4 times 7, and 7 by 7. So that's just 4/7i. Please note, this is the final answer and not the one before, not that one. Pretty close. Okay, number 80. 3 plus 2i over 4 plus 3i. So what I did is I actually multiplied by the conjugate. 4 minus 3i, top and the bottom. That's what I did. For the bottom, for the top, you can look at the details here. Combine like terms. And here's the answer. Once we split the fraction into a real part and an imaginary part. And that's how you divide number 80. And let me see. Oh, and that was it. I guess we're done with this section. And nothing too complicated. I hope you were able to follow everything we did. And with that, we are done with section 10.8. So let me bring this up. Okay, goodbye.